Next up is Dr. Behnam Jafarpour from University of California.
Okay, thank you, Andrew. And, hello. I'm Behnam Jafarpour from the University of Southern California, and I'm one of the chairs working on application of data science to subsurface energy systems. Before I start, I wanted to thank the energy simulation team for organizing this, also the TU Delft colleagues here who did the work in organizing this far away from home. We actually had a competition that chose between LA and here in Netherlands, but you won. Okay, so let me go ahead and start by showing a snapshot of what we do in my lab. So basically, we are looking at developing customized data solutions, data science solutions for subsurface energy systems. And my general interest really lies at the interface of data science, system theory, and subsurface flow systems. And the application areas are conventional and unconventional oil and gas reservoirs, as well as geothermal reservoirs and geological CO2 storage. And more recently, our focus are shifting a little bit toward geologic CO2 storage, and I will tell you a little bit more about that in a few slides. So in terms of specific areas of work, we actually look at description and characterization of complex geological systems. Most of our past work has been focusing in this area, has been focusing on coming up with low-dimensional descriptions for high-dimensional geological models that are used in these applications. And that kind of facilitates what we do next, which is integration of data and quantification of uncertainty for these systems in low-dimensional solid spaces that we describe in the first area. And then another topic that is also very close to my heart is field development optimization in any of these specific areas that I mentioned. And we mostly are interested in improving the performance of these systems, and more recently, there has been some sort of shift into also looking into environmental and risk aspects to see whether optimization tools can be used to mitigate risk. And that's one of the areas of focus for us when we move toward geologic CO2 storage. And the last area, which is really a tool for us that we are trying to leverage to develop new techniques and algorithms to kind of solve some of the challenging problems that we have in the other three areas that I mentioned. Okay, next. All right. So I mentioned a little bit about geologic CO2 storage. We are collaborating with Penn State. We are trying to put together a center, a National Science Foundation Center on what we call CO2 Smart, CO2 storage modeling, analytics, and risk reduction technologies. And this is going to be basically a center covering a broad range of topics related to geologic CO2 storage, from site screening, characterization, all the way to multi-physics simulation, monitoring, data analytics, uncertainty and risk quantification, as well as economics and optimization. And this is going to involve close to 20 faculty across the universities, which will come from engineering school, geoscience program at Penn State, as well as the School of Law and Policy and Economics from the two universities. So that's what we are looking forward to, and hopefully we should have this started sometime early next year. So before I start the actual topic, I want to also mention two of my students who are presenting posters here. One of them on a data-driven geologic CO2 storage monitoring, and that's Yingxiang Liu, and physics-guided deep learning for geologic CO2 storage, and that's Zhen Qin, and the poster outside, and if you wanted to check them out. So now the actual topic of my presentation today is active learning for efficient well control optimization. And this is where I want to thank Dennis for the presentation earlier this morning, because that was the perfect introduction to what I want to talk about now, which is some of these field development and management workflows that we have are very complex and involve intensive computation and a huge number of simulations that we have to run. And that's where some of these what we call proxy or surrogate models can become very helpful. And what I will try to describe here is how do we approach this problem, and from coming at it from an AI perspective and neural network kind of models. And one of the key takeaway messages that I would put right in the front of my presentation is really adapting these algorithms toward the application that we have and toward the objective of that of developing these models, right? And that hopefully will come across throughout my presentation. So our objective is really developing data science solutions for subsurface system. And what I want to emphasize here is really the bottom part, and that's the importance of domain knowledge. And domain knowledge can come in the different forms. It can be the physics, and that's why you hear physics informed, physics inspired, physics based, or any other form of that terminology. But that's not just it. I think in addition to physics, experience and knowledge about subsurface system is also very important. And that's something that and also experience about workflows that are involved. What is exactly you're trying to do with the model that you're developing? And that plays a significant role in terms of the efficiency of the tool that you develop. So with that, you saw something similar to this from Dennis's presentation. This is basically showing a closed-loop reservoir management workflow. And as I mentioned, and Dennis also had in his presentation, it involves very complicated, complex workflows and many, many simulation runs for different purposes. You have a loop here that focuses on model updating, integrating dynamic data into your models to improve their prediction capabilities. And then you have another loop, which is shown in red here, that takes care of decisions for either short-term decision or life cycle decision in terms of how to operate the field or how to develop or introduce a new well into your field. Now, in many of these kind of algorithms that are involved in these workflows, the full-scale simulation will be overkill. Because when you run full-scale simulation, you're getting many answers to many questions that you can ask about the reservoir. But in the particular application and objective that you have in mind, in this particular use case that I mentioned now, is optimization, right? When you look at that, you may not need to know the answers to many other questions in terms of fluid distribution, in terms of the pressure field, etc. What your objective might be in that particular use case is, what is the response, the oil production response of this field to some perturbation to the wells that I introduce in terms of injection or production quantities, right? That's what you want to know. And for that, you don't really need to run full-scale simulation. That's where fit-for-purpose modeling becomes attractive. So in recent years, people have started to look into AI and machine learning to develop those kind of proxy models. That the idea is that you spend some time to train these models offline, and then once you bring them in line, your predictions are almost instantaneous, right? And that's what we've kind of tried to leverage in order to build some of these proxy models. And we were approached a few years ago by CRC to actually develop a practical tool for their day-to-day water flood management. And this is a field that they were working on in Long Beach. And this area is very popular for water flooding, and most of the time, the water cut is above 95%. So there's a fraction of oil that you're producing, and depending on the oil price, that can be lucrative. So what they wanted to know, and you can see the field is very complex, and there were hundreds of wells in this field. And what they wanted to know was whether we could come up with a tool, a machine learning based tool, that would help the operators to just, if they want to facilitate their daily operation and decisions. They did have reservoir engineers in their main office, and they would do all sorts of modeling, history matching, and model updating for these models, but those would happen every 6 months or so, right? So, but they wanted to have a fast tool for prediction of some of the operational changes they wanted to introduce. So that's what that's when we started to look into these kind of problems, and basically they did have this model. And what they wanted to do, they wanted to have a simple model that would not require a lot of expertise to run, and they could use that to improve their operations. So for us, developing a proxy model meant that we need to generate simulated data from this model, and that's also costly because these simulation runs are quite expensive. So what we did, we actually did we defined a few different tasks with that field. And one of them, in this case I'm showing, is understanding the well connectivity. Can we develop tools, an approach by using data from the field to actually give us some information about how the wells are connected, and that would be helpful in terms of predicting the production from the field. What I want to talk about, though, is basically looking into predictive modeling in terms of production, and then using predictive models of production to optimize the performance of the field in terms of oil production. And what you see on the left here is a typical workflow that has been used, and you see a lot of similar work in the literature, where you start by generating a series of well-controlled scenarios that you provide to a simulator, and the simulator will give you responses to oil production for each of those different scenarios that you have in time. So basically, the simulation, what it's really doing for us in this case is labeling the data. So we have unlabeled data, and the simulation is a very expensive way of creating labels. And typically, if you talk to anybody who does machine learning work, they know that labeling data can be quite expensive. And in this is no exception. In fact, one of the examples that shows how expensive it can get. And you need a lot of data to make a reliable model. And then once you use that and you go through the training, let's say you use a neural network for this, and once you develop this neural network model that is trained, then you use it for optimization. So this was our starting point. We looked at it and said, okay, we generate some data, and we train a neural network, and we go after optimization. We'll see what happens. So I'll bring us back to a very simple example to describe what is actually taking place during that training process. So what's happening is that each of these simulations, or labeling schemes, is really providing a data point on this simple example showing the response surface of the model that we are working with. So basically, for each simulation, you get a data point, and then machine learning, what it's trying to do for us is really to understand what this surface looks like, because we want to do optimization on this surface. You want to go, in this case, you want to go, let's say, to a minimum point on this surface. So what you will see is that I'm showing a reference case, in a simple problem, and a proxy that is based on 5 simulation runs, right? And I'm going to increase the number of data points and see what happens to what the machine learning is trying to kind of give us as a solution to this response surface. Hopefully this will work. Okay, so the number of samples is increasing, and so does the prediction from the machine learning algorithm. And you can see that at some point, these numbers are going up, the number of simulation runs are going up, and you get a better shape, better approximation of what the actual surface looks like. So we said, okay, so we do that. So we went through this process, we increased the number of samples, and we got a good kind of representation. We did a validation of our training process. Everything looked very good. Then we went to optimization problem. And in the optimization problem, what we did, we performed the optimization, and throughout the iterations of this optimization, as the input was changing, the decision variable is changing, what we did, we also did some monitoring with the simulation model to see how the proxy is performing. For the first few iterations, everything was fine. But then we began to see divergence between our proxy model predictions and the simulation model. So this was for quite a few weeks, we were actually looking into what could be the issue. Is there a systematic underestimation, overestimation? What is happening? So if you think about it a little bit, one of the main reasons something like this can happen is that when you do optimization, and that's what I meant by use case and the application you have for these kind of models, you're trying to start from a solution, and let's say you're trying to maximize oil production. You're trying to start from a best engineering solution, and from there you want to have incremental improvement until, let's say, you get a convergence to a maximum point. But what is really happening, you're moving away from the training data that you actually developed for that neural network model. And as a result, you're systematically forcing this algorithm to push your proxy from interpolation toward extrapolation problems. And that's why I asked that question from Dennis after his presentation. And that's what's taking place here. And if there's one thing we know about machine learning techniques, is that they're not very good for extrapolation. In other words, you give it training data, as long as you stay within that training data, they work fine. But as soon as you step outside, that's where you begin to see limitations of these methods. So what we did, in order to explain this, we said, okay, let's take a look at our training data. Let's take a look at the optimization iteration and see what's happening. And what we observed was that exactly what we were thinking, that these were the type of training data that we were using, and the value of the objective function was bounded within a certain range. Then we started the optimization. After a few iterations, we started moving outside this range. And when we get toward the final iteration, we'll see that the kind of patterns that are introduced as input into this proxy model are very different from what we had in the training process. So what were we supposed to do now that with this understanding that what is taking place? There are people who actually suggested that what you can do is you can actually go ahead and retrain your model once you get to these areas where you see big divergence. That could be a practical solution, but the downside with that is that, number one, this process is front-loaded with a lot of computation that we could argue is wasteful. Number two is that by the time you react, it might be too late, because the optimization with a wrong prediction can take you somewhere you don't want to be, right? So that's another challenge that you will have with that approach. So our approach to this was, let's take a look at what we're trying to do. On the left-hand side here, I'm showing the reference response surface and what a typical optimization algorithm does. It starts at some point. Let's see if I can show this. Yeah. It starts at some point here, and with the iteration, it begins to converge to a local solution. That's a typical behavior of an optimization algorithm. If that's our understanding, then does it make sense to generate this much data and try to get a very good understanding of a big response surface area that is not even used, right, in our analysis? And that's a typical problem. In any optimization problem, local optimization problem you go to, you're really following a specific path during optimization to converge to a solution. So with this strategy in mind, and that's why I make a point about really understanding what is happening in your problem and trying to adapt your machine learning approach to take advantage of that. So with that, what you can do adaptive sampling. So instead of front-loading your computation and generating a lot of data at the beginning, you can start with very few samples where you are in the iterations, and then do your local prediction during optimization. And every few iterations, you can add more samples. Sometimes you have to actually remove subsamples because those samples may not be helping you anymore, right? So you have to actually do that's what the terminology active learning and adaptive sampling comes from, because sampling is done based on the use case and the application and the algorithm that you're using. So, so what we conclude from here is that without adaptivity, you end up having a very inefficient offline training algorithm, and you may have to retrain a few times before you actually get to a good solution. And the fact that you're not taking advantage of the use case that you have, so some sort of customization is needed in order to maximize the utility of these approaches. And the accuracy and reliability is an important issue when you look at these proxy models that we develop. So how do we do this now? So by leveraging this adaptivity scheme, we try to drive efficiency and try to make the surrogate models more reliable. So in this case, what will happen is that now your sampling will be based on the optimization feedback. So during the optimization, you look at where you are on that path of the optimization, and you sample according to that. What I mean by sampling is that you generate the control strategies based on where you are. You pass them to the simulator, and the simulator will give you the labels in that neighborhood. And then you take your next step in the optimization algorithm. So if I want to basically close that gap, you will see what I have in here compared to the offline training is now I have a strategy for sampling. And I use that strategy to generate a subset of samples that are useful for the algorithm, as opposed to starting with sampling uniformly across the response surface. So that's basically the strategy that we used. And we applied this to also other water flooding examples, benchmark examples that we have. This is another example that has been used in the literature quite widely. And what we saw was that with active learning, you could converge to better solutions faster compared to the offline training where you front load your computation and you train these models and then use them for optimization. More recently, we have been looking into the application of these kind of strategies for geologic CO2 storage. And in this case, the objective function really could be user-defined. In this particular example we're showing in here, we looked at minimizing the free CO2 after injection in the storage formations. But there are other examples we have where you look at, for instance, minimizing the increase in pressure. So these are applications depending on what your objective is. You can define those the objective function and try to go formulate an optimization problem and solve them. But in doing so, I think it's really important to understand how to set up your training approach for developing these proxy models. So this is an example showing basically application of this active learning approach, where the top part on the right-hand side is showing the saturation when you have a uniform injection into these 4 wells that we have. And then the bottom part is trying to minimize the free CO2 in the formation, and the results that you see basically trying to minimize the CO2 under the cap rock. And in this case, the offline approach is the performance is going to look something like what you see on the left-hand side. Compared to the comparing proxy to the simulation performance, you can see after a few iterations the divergence begins, and that divergence is hard to compensate for. With active learning, you basically try to stick close to the optimization path of your algorithm, and that's how you keep the fidelity of your model at an acceptable level. So with that, I want to conclude. And basically, these ML-based proxy models can facilitate complex fit optimization problems by reducing computational overhead. In optimization problems, offline training approaches can result in poor extrapolation performance, which is a widely known property of machine learning techniques, and that can lead to incorrect or suboptimal solutions. By using active learning, by adapting basically your training process to the application that you have, we can enhance the computational efficiency and the optimization outcome as well. And we have seen promising performance for water flooding examples and geologic CO2 applications. And as I mentioned, the takeaway message here, really adapting your machine learning framework to the use case and the objective that you have in mind. So with that, I want to thank my lab. And it's in this particular case, Junji is the person who has done most of this work, and our sponsors, including Energy Simulation. And thank you for your attention.
Thank you, Behnam. Questions, comments? Okay, nothing online either. So, oh, okay, there's one. Dennis.
Just to give you back the questions, but we are doing more or less the same thing. We don't call active learning, but it's the same. I wonder if you have a criteria to discard points that are not useful anymore in the process. Do you have a way to know how to do it? Because we didn't figure out yet.
Yeah, it's more of a rule of thumb thing that you have to come up with, and from one example to another example can be different. So a few things we have looked at. For instance, even there are parameters that you have to tune. How many, let's say, at which iteration you introduce new points. It could be at every iteration. It could be at every 5 or every 10. That's really, it depends on. If you want to kind of test it, you have to run a full simulation to see how far away you are, and every few iterations if you do that. Now, at some point, of course, the example I showed where you look at the response surface, you can visualize, but for a real problem, you can't do that. So, but you can define a metric that shows the distance between the training data, not that particular example, the range of training data that you have, the range of objective function that you have, and define a distance between where you are and where that range is. And unfortunately, nothing really as a rule to use, and we have seen different results for different examples, from simple example to very complex example. That's part of the tuning of the algorithm.
Yeah, that's more or less the same we are doing. Just as we add, for example, 20% more points, we discard 20% of the worst points and so on. So we keep going. Yeah.
I think the removing point, I think you have to be careful with that, because points that are there, you have already spent a simulation on them.
They
so
can be useful,
it's good to keep them if they are not misleading the proxy model. And that can be done, in an effective way, kind of trying to include and exclude that data to see what kind of response you get. Kind of validation approaches.
And we are trying also to do the opposite, not to use the proxies to find the answer, but to discard the worst regions in the research space. So that's another policy. Yeah. Okay, thank you.
Yeah.
Okay. So once again, thank you.
Oh, okay.
So Giovanni, you may not want to remove a point, right? For your betting plane. Sometimes it's important to look at some of the extraneous points to see why it happened that way.